I usually go right past this first opening slide, but I think it's actually something to talk about while we got it. This is the top half of a posit ring. And it takes if you look at the way that binary numbers count up on the outside, they overflow as soon as you get to 0, 1, 1, 1, 1, 1, 1. At that point, the carry bit turns it into a negative integer. And that flips it over, and then you count back down. And the fundamental idea was, why not map real numbers to that pattern? Now, the other part of the ring you can't see is numbers that are less than 1, and they're like the reciprocals, the ones that you see here. So keep that in mind. I will build up an explanation for this. Okay, here's my thesis. The slowdown of Moore's law and the needs of artificial intelligence have made us realize that IEEE floating point format is really long in the tooth. It is obsolete. And most people don't realize that it was actually a proprietary Intel format from 1977. It was not designed by a grand committee of mathematicians or anything like that. It was very proprietary to Intel, and they hijacked the standardization process and made everybody else conform to what they'd built into a coprocessor. IEEE floats waste storage, bandwidth, energy, and power. The POSIT format was introduced in 2017 as a new way to compute with real numbers, and they're designed mathematically to meet engineering goals. So here are the things that a number system should have. And you can get up to like 4 times gain in terms of just like 2 turns of Moore's law, doubling performance or cutting in half the amount of power you need or the money you need, but you can actually get better answers with fewer bits. So this is a watershed, and it's a revolution, and it's well underway. The established companies will be slowest to adopt a new number format. This is a big wrenching change, and there's a lot of inertia. But the smaller companies are starting to realize that they can be very competitive with this. So, given that computer arithmetic is possibly one of the most boring subjects in the known universe, I do try to pep this up with as many metaphors as I can and keep your interest going. There's a game called 20 Questions that was actually a parlor game in the 1800s, and it turned into a radio show in the 1900s. And the idea is, identify a mystery object with no more than 20 yes/no questions. And they had things, someone who was envisioning Winston Churchill's cigar or the pencil that I'm holding, things like that. But yes/no answers, of course, are bits. So if I say, I'm thinking of an integer between 1 and 30, and you only get 5 questions. Any computer scientist would know exactly how to do this with divide and conquer. So is it 16 or larger? No. Okay, put down a 0. Is it 8 or larger? Yes. Add a 1. Is it 12 or larger? And so on. Each time you build a bit string, as you read it from left to right, you get more and more information homing in on what this number could be. Is it 11? Yes, you win. Now, that is binary for 11, right? How come real numbers can't work like this? That's what I wondered. 11 in binary. This is how analog to digital converters work, if you're familiar with them. Always comparing against a given voltage. And that's why every time you want one more bit out of an A to D converter, you have to double the size of the hardware. What if the game starts with, I'm thinking of a real number? Where do you even start? What should be your strategy? I see this line of reasoning a lot. Oh, you cannot represent all the real numbers on a computer because there's an infinite number of them, and computers only have a finite amount of memory, which sounds very reasonable, except there's 2 things wrong with that. First of all, how come it didn't bother you about integers? Because there's not a lot of those too, right? There's an infinite number of integers, and yet it's only when you start to think about real numbers that you say, oh, that might be really, really hard. I can actually show you how to represent all real numbers with 3 bits. Next slide. These are the projective reals. Imagine that you have a circle and you put a light bulb at the top of it, and it projects all the points in the circle down on a line. Well, I can map 1 to 1. The top of the thing projects out to infinity in either direction, so that's plus or minus infinity, and 0 projects just straight down. But now that infinitely long real number line simply looks a lot more finite. It's a circle. So it looks like there's some hope here. Next step. Think of it as a dot, a tube, a dot, a tube, and the dots are exact values like 1, -1, and 0. And that thing at the top, I'll call it not plus or minus infinity. I'll just say not a real, and it'll be my That'll be my umbrella for anything that's like 0 divided by 0 or the square root of -1. Anything that is not a real number goes right there up at the top. Then you've got these ranges, like exactly 0 and 1 in between. It's the range from 0 to 1, not including the endpoints. The range from 1 to infinity, not including the endpoints. Okay, so you can make a table like this. All the ranges end in the bit 1. All the exact values end in 0. All the negative ones start with a 1. All the positive things start with a 0. So there's a system here. And you give me a real number, I can map it to that ring, 3 bits. Square root of 2 and pi will be in the same place. They'll be in the top right-hand quarter. So it's not very accurate. But hey, I only got 3 bits. And I did include everything. So if you add an extra bit now, hey, the green square went away. That's great. I was having an artifact on the screen. It went away. Now you could say put the number 2 in between 1 and infinity, or you could put the number 1/2 between 0 and 1. And this is kind of cool because you can negate simply by revolving about the vertical axis. Perfect negation. Well, 2's complement integer can do that. But if you revolve about the horizontal axis, you can reciprocate. You get exact reciprocals. So that makes division as easy as multiplication. Just like subtraction is just as easy as addition on a computer. Okay? Now, it didn't have to be a 2. We can put all kinds of numbers there. Depends on how aggressively you want to raise the dynamic range. I'll talk about that a little bit more later. But like I say, reciprocation is really easy. And this is called a type 2 universal number. That's the interval form. Now, if you actually round, here it is with the ranges, see? Like between 2 and infinity. Replace that with the number 4. Replace all those ranges with a midpoint number. And now it's like rounded floating point arithmetic, where you always have to pick an exact answer, even though it should represent a range. And I have to give up a little bit on that perfect reciprocation because I've got 3 halves up here. And I got 3/4 down there. Oh, good, I've got a cursor. And so the product of those two is 9/8. It's 12.5% too high to be a reciprocal, but it's close. So all the reciprocals are only perfect for powers of 2. So it's a really good guess. If you're going to do a calculated reciprocal, the first thing you do is just negate all the bits after the sign bit. And that's your very, very good guess for a first start. You can correct that with a little bit of maybe a little Taylor series or something. So appending a 0 bit does not change the represented value. That's one of the rules. Just like decimal. So I say 0.375, I say 0.3750, same number, and you can do that forever. But if you add a 1, then you've got something in between 2 exact bits. So they keep growing. So if you add a 1 bit in between the top of the thing, the infinity, and x, insert 2x. Between the bottom, on the bottom, between 0 and x, insert half x. Otherwise, you insert the average, like between 1 and 2, you insert 1.5. So that's how you grow the ring. The cool thing about this is that even though I'm adding bits on the right, I'm increasing the relative accuracy on east and west, but I'm increasing the dynamic range on the top and the bottom. Now, with floating point numbers, you have to disentangle them, and oh, here's the exponent bits, and they're biased, and we'll have to do something to them, and here's the fraction bits. It's stuff like that, very messy. This is just elegantly adding more information to the right. These are posits, 4-bit posits, very low precision. Posit, I started calling these guesses because anytime you're rounding numbers, you're guessing your way through a computation. But some people thought calling them guesses was pejorative. So I said, okay, let's call it a positive because that's a statement made on the assumption that it will prove to be true. It'll be a little bit more optimistic. I also like the fact that it was 5 letters, so you can take the word float out of your code and put posit in it. It won't change the pagination or anything like that, which guess could do that too, I guess. Okay, everyone's out of bandwidth. I think if you're designing anything in computer architecture, you realize, oh my God, moving bits around is way more expensive than doing any kind of arithmetic on them. So why am I so concerned about arithmetic? Because I want to move fewer bits. I don't want to move 64 bits for everything. Use double precision everywhere. That's what the waste is. So if I can get that down to 32 bits, if I can get AI training from 16 bits down to 8 bits, it's like doubling, it's more than doubling the speed. The training of ChatGPT cost hundreds of millions of dollars in electricity alone. It's trained in middle of Iowa where they could add access to all this wind energy. It was like the lowest cost per kilowatt hour, but it was still hundreds of millions of dollars, many megawatts running for months. So any excess precision you have in your algorithm is wasting memory, bandwidth, energy, and power, and time, and money. So programmers use excess precision so they don't have to think. They just throw whatever is like, maybe it's got native support for 64-bit floats, so just use those. Or they maybe don't even have something like 16-bit precision to use. It would be more trouble than it's worth to try to use a lower precision, although that's changing. I tell people this is like you have a car and you don't know what it's worth, but you want to insure it. So you insure it for $5 million. And then you are really upset when you see your insurance premiums. But that's what people do when they use 64-bit floating point everywhere. So the current methods of designing number formats come from a time when operations were expensive and moving data was practically free. And you took more time to do a floating point operation than you did to fetch something out of memory. Now it's more like 200 to 1 the other direction. But what if we could get better answers, as I say, with fewer bits? So posits work like 20 questions, but for real values. Is X less than 0? No, put it down to 1. If it yes, put down a 0. If it is, then put down a 1. Is it less than -1? Is it more than -1? More than +1, so on. And now you've got this something compared to a constant. That's that thing in the northwest corner. I use 2 to further divide it, but you could use a different number. And now after 3 bits, you already know a lot about where that real number is, and you've done it from left to right. There's a lot of logic to this. If you have, I know you're all great scholars, but maybe you've heard of Dedekind cuts in mathematics. Aha, guys nodding. Yeah, Dedekind cuts. These are based on Dedekind cuts. The regime format takes some getting used to. You're used to being able to do tick marks like Roman numerals, 1, 1, 1, 2, 2. Is the most primitive way of recording numbers there is just putting down tick marks. How would you record both positive and negative numbers with tick marks? Let me show you how you can do it with bit 0s and 1s. Now, by the way, I'm going to talk about these zeros as ghost digits. So you write down explicit digits, but when you stop, it implies that everything past that is 0 digits, whether it's in binary or in decimal. I have to have a name for them, so I call them ghost digits. All right, here's some bit strings for you. Now, 3 zeros in a row is like a really fine steel wool or a really tiny tool, right? 000. 00, not quite so much. You can terminate it either by hitting the opposite bit, a 1, or by hitting the end of the number of bits you've allocated. So 001 represents the number -2 because it's 2 zeros in a row. 01 represents -1 because it's just 1 0 in a row. But that top one, 3 zeros in a row, it doesn't end. It's got an infinite number of zeros past that. So it actually represents the number -infinity. So that's kind of interesting that this very primitive unary method can actually represent the number -infinity. But over on the other side, I subtract 1 from the run length. So I have a 1 in a row followed by a 0 stops it, but that represents the number 0. And so it's always k minus 1 if the first bit is 1. Otherwise, it's -k. That's the system. And this actually follows the rules for 2's complement arithmetic. It's like you took Roman numerals and applied 2's complement to them. If you can get your head around that. They're tally marks, but they're signed. Okay, so this means I can express the value of a posit in a single formula. Later on, I'll show you what it looks like for IEEE floating point. It's like 13 cases. But S is the sign value, 0, 1. F is the fraction. And then you multiply times 2 to the scale. Scale is the this thing right here. R is the value of the regime, which could be, as I say, -infinity. If you put -infinity in here, if it's 0 followed by all zeros, this formula gives you 2 to the -infinity. That's 0. If you put in 1 followed by all zeros and compute this formula, you get -2 to the +infinity, which is -infinity, which is not a number. It's not a real. So I use that for not a real anything. Anything is not a real. Any indeterminate form. So let's talk about floats a little bit. I say that IEEE standard floats are weapons of math destruction. They are so bad They were created in Intel, actually 1976 for the first IBM PC. It was going to have a coprocessor right next to the main processor, optional. For $150, you could buy this coprocessor, and it would trap floating point instructions and execute them much more quickly than this little I guess it was the 8088 processor, 8 bits wide, could do it. So the idea of a floating point number is you carve things up into bit fields and say, this is going to mean the exponent, this is going to mean the fraction, this is the sign, this is the sign. And they can put them all over the place, different places. Okay. So there's no guarantee of repeatable or portable behavior in that standard. You can get a different answer, even on the same machine running a few seconds later, because it's just so completely unpredictable. Computations change when you parallelize them. If you wanted to add a bunch of numbers, you're going to get a different answer if you add them in a different order, unlike mathematics, where you have an associative principle of associative property of addition. You don't have that with floating point addition. This has caused us a lot of trouble. Okay, though the 32-bit form of IEEE floats is so inaccurate that it does kind of lead people to use 64-bit floats. It's just not quite enough. If you had like 36 bits, you could probably do most scientific computing, but instead you double it all the way to all the way to 64. I have to laugh when I see people falling asleep in the audience. Anyway, I know this stuff is hard to listen to. Illogical. There are numbers that are not equal to themselves in IEEE floats. What they, instead of not a real, they use not a number, even though complex numbers and imaginary numbers are numbers. That's what it says right there. But they call them not nan, not a number. And nan is not equal to itself. And there's like 9 trillion ways to say something is nan in floating point, so it's very wasteful. A equals B doesn't mean that the function of A equals function of B. Standard says positive 0 is equal to negative 0. Now, anybody who believes in something like positive 0 or negative 0, their math education has failed them. There is no sign to a 0. It's 0. But the reciprocal of positive 0 is positive infinity. The reciprocal of negative 0 is negative infinity. And those are about as different as you can get, right? So very poor handling of overflow, underflow, and if you come up with an error condition, it's quite possible that operations on that will make it disappear. It won't last to the end of the computation. You'll see a perfectly normal number. Like if you take 1 to the power of nan, you get 1. If you take nan to the power of 0, you get 1. It looks like everything's fine, even though you did something really wrong while you're at it. Let's see. Okay, the dynamic ranges are just really, really wrong for what you need for scientific computing. This is what IEEE looks like, and I did a 16-bit form of it, but all you have to do is lengthen the fraction and lengthen the exponent, and they all follow the same pattern. They got all these exceptions that have to be tested for in hardware or software, and they produce quiet not a number, which just keeps computing, signaling not a number, which says stop, don't do anything more, call the operating system, or subnormal numbers. Those are real cute. That means that you've got accuracy that fades down to 0 over on the left-hand side of the accuracy graph, but I'll show a plot of that. Otherwise, you got this normal float. Now, there's a dirty little secret in the computer business that right around 2000 to 2005, chip designers started saying, you know, it's really expensive to handle all those. So let's just trap them to software or microcode and handle it with a software handler. Otherwise, we'll just assume everything is a perfect little one-liner, like my posit one-liner, and that's fast to compute, and we'll support that in hardware, and we'll claim we can get a floating point operation every second, every clock. But it's not true, because if anything goes wrong, and these cases here are not that uncommon, especially the subnormals. These guys happen all the time in scientific computing. So you can actually tell what somebody's computing by how long it takes to compute it, which is a side channel attack. And it's been used to actually break into calculations, figure out what's going on. And what about reproducibility? Well, if you do things on the cloud and you get different results in each run, that devalues your computations. Huge scale calculations make reproducibility harder than ever before. When you submit something to Amazon Web Services, a big HPC calculation, you're not going to expect to get the same result every time. So what used to be a small little rounding error discrepancy, it can cause a butterfly effect that really destroys your answer. And then you waste all this time trying to figure out, why am I getting a different answer? Was it a bug? Was it a soft error? Or is it just do that? And most programmers say, oh, that's just called floating point drift. They don't know exactly what causes it, but they've learned to live with it. They shouldn't. Here's what it does for climate prediction. So I believe curves of the same color are runs on the same program with the same starting assumptions, or very, very slightly perturbed starting assumptions. And look at the wild variations you can get from the butterfly effect in the beginning. Now you show this to someone you're trying to convince that global warming is important, we should do something about it. And they say, well, I think you can make this program say whatever you want. This is garbage. They will reject this because it's just not reproducible. Now, here's why linear algebra is not portable with floats. Suppose I've got a 4x4 matrix, and the second row is these four numbers. 2 to the 26 it's not huge. It's like 64 million, and negative 2 to the 27th, and so on. And I'm going to multiply that to get entry number C22, the way you multiply matrices. So you're going to need, all those values are exact, even in single precision. And even if you multiply them, they're still exact. All those, that's the four products that you need to add up, okay? And you use, let's suppose you use double precision, because that makes everything fine. You don't have to worry. If you use double precision, you'll never get any rounding errors. It's so accurate, right? No. Parallelization changes the order of summation. You could do pairwise collapse. You could sum from left to right. You could sum from right to left, and so on. So there are actually 15 different ways to add up four numbers. They are least commutative. A plus B is the same as B plus A. So it's not 4 factorial, but it is 15 different ways, depending on how you group the parentheses. Here's what they never taught you in computer science courses. All over the country, this is true. That floating point rounding is just really treacherous. You can get 0, 2, 1, or -1, 4 possible values out of that summation, depending on what order you do it in. And since it's a dot product, getting 0 says, oh, these vectors are orthogonal, which could be really important for certain things. But in fact, the correct answer is 1. So if you parallelize things, you can get 4 different values, and that makes people worry about their parallel program, because it gives different answers in the serial program. And they think, well, parallelization is hard, and I don't know where this bug's coming from. So let's just go back to the serial program. It stops people from using multi-core. So let me just state 11 design principles for designing a number system. The distribution of values that you can create with the format should closely match the ones you need for a calculation. Simple enough. I mean, how can you argue with this, right? It's just like the letters of the alphabet you would need to spell something. There should be no redundant bit patterns. Every bit counts. Every bit pattern counts. There should be no hidden modes of operation where somebody's changed how it rounds by setting a processor flag, and suddenly you're getting different answers, but you don't know why. Everything should be determinable by looking at the source program and the data, period. Not your make file, not any little settings you made to the compiler. That should not have any effect on the answer. It doesn't with integer operations. Why should it do it for real numbers? All the math operations have to be correctly rounded. Currently, you're allowed to not round correctly e to the x, logarithm, sines, arctangents. You can be off on those because they thought it was too hard to get those correctly rounded. That means if you use the Intel math library instead of the GNU math library, you're going to get different answers. The exact same program. It should be very easy to change precisions, just like it is for integers. Integers, you just add zeros in the beginning, same integer. If you want to shrink it, well, you might overflow, but it's just a matter of stripping off the zeros. The error results, you get a bad error, a bad mistake, like what I call NAR, not a real. That should propagate to the final output. So you see something went bad. Do not trust this answer, it's wrong. And it should also be simple to build in hardware and fast. And when I say fast, I mean fast per watt, because that's what really matters, is the power efficiency or the energy per operation, same thing. Now in the nice to have category, it should be easy to scale to any number of bits, not just 8, 16, 32, but no, 17 bits, 23. If that's what you need, you should be able to scale it 1 bit at a time. And real numbers should be ordered like integers with the same bit strings, the way I showed you in that initial arc, because now you don't need a separate unit to do comparison operations. You've already got it. If you can compare two integers, all your real numbers compare exactly the same way. That not a real thing acts like negative infinity. It's less than every real number, and it's equal to itself. Negating a real should be the same as negating it as an integer. Well, if you got two's complement, just flip that thing around the vertical axis. And the results of application computations should be as close to what they would be if infinite precision was available. Just give me good answers. That's kind of a squishy goal. I almost leave it off because maybe it would be nice to have 10 design principles. That's a nice round number. But you have to say it has to give really good answers. Whatever it does, it should do that. Now, I believe I'm the first person to set down these design principles. I've looked at the committees that design number systems, and their only design principle seems to be, what's the simplest thing we can get away with that will work? What little modification can we do to what we've been doing? And this is where the AI people are getting their number formats. They're taking old-fashioned floating point and they're trying to stick things onto it that will let them use 8 bits, like by scaling by a secret number over here and things like that. No, the IEEE standard, if I go through these 11, it fails every single one of these goals. Let's start with that one about distribution. What reals should we seek to actually depict? In studies that have been done at national labs, and this is an ongoing effort, you get the kind of a log Gaussian. You get the bell curve centered about magnitude 1, and it's very rare to go outside 10 to the minus 13th to 10 to the 13th. Now, the people who do like cosmological calculations and n-body calculations on the solar system, they're in a different category, and they need a bigger range. Okay, because I can't even do equals mc squared with that range. I'll overflow. But for an awful lot of basic blocking and tackling, linear algebra, scientific computing, that's all you need. Now, what does single precision give you? It gives you that. And what's that ramp over in the left? That's the subnormals, where they gradually slide down to no accuracy at all. There's nothing comparable on the right, although there could be. They decided not to do that. So already you see the waste. You're only using a tiny fraction of the possible bit patterns. So you see how you could get two phases of Moore's law just by getting rid of this and actually making it fit correctly. Now, the 64-bit floats, I can't even put them on this graph because it would extend from like over here to over here, even though you still need only this little Gaussian. That's like 2% of what double precision can do. It could go like 10 to the 300th to 10 to the minus 300th and even beyond. So you don't need flat accuracy. Usually the bigger a number is, the less you care about how many the digits. Like if I say Alpha Centauri is 4.3 light years away, you probably don't want more decimals than that, do you? Really? For any what for? It's just really big. And same thing for things like only a micron across. When you get either extreme, you don't care about the significant digits nearly as much. It's only things that are close to the human range of like 1/10 to 10. That's where you really need accuracy in things like pi and square root of 2. So posits have a tapered accuracy. They make a tenth, and they've got really big dynamic range, bigger than floats, or they can have bigger than floats. So that's just, they've got extra bits, and they are something like an order of magnitude more accurate for 32-bit calculations. There is a, let's see, that's a 5-bit posit ring. Now I've finally shown you the bottom part. And as I say, it allows you to usually cut in half the number of bits you need to do a calculation because they're so much better behaved. Now, let's see. Who here has heard of a Hilbert matrix? Wow. Okay, I finally stumped him. All right, a little bit. I first thought this was some contrived thing. It's not. It actually arises if you're trying to fit an arbitrary function to a polynomial with statistical methods. You get this matrix that has 1, 1/2, 1/2, 1/3, 1/3, 1/3, 1/4, 1/4, 1/4, and so on like that. And just all the reciprocals going down the anti-diagonal. Now, these are beastly to solve in any numerical system. They're very prone to rounding error. They have what's called a huge condition number. This is like half a million is the condition number, even of this little 5x5. So it's super sensitive. If you tweak any of the inputs, you get massively different output. It's unstable. And yet it's got nice properties. It's symmetric. It's diagonally dominant. So we're going to do a test by seeing by entering these numbers, but there's a problem. You can't represent 1/3 as a floating point number, or as a posit for that matter. You can't put a 3 in the denominator. So scale it up by 315. Instead of solving this times its inverse equals I, you say this times its inverse equals 315 times I, and now I can scale everything up, and everything is exactly expressible by both floats and posits. All right, I do a standard Gaussian solver, lower diagonal, lower transpose decomposition, just like you do in grade school. You eliminate the variables down, and you get this result. And the inverse is like 3 or 4 decimals accurate for floats with 32 bits. You get a much better job with the posits, but it's actually about 400 times as accurate. But posits have a trick I haven't mentioned yet. They have a fixed point register that is 16 times as large as your working precision. So if you had like a 16-bit posit, a 256-bit fixed point number can store the smallest posit squared and the largest posit squared, and you can do exact dot products, no rounding, associative addition, restored. And you can do them in parallel in any order and get the same answer for the first time. If you use that to correct the calculation by computing, okay, compute h times h inverse, how far off were we, solve again, add the correction factor, and it nails it. The correct answer is all integers. So you really know whether you got it or not. There is no way you can do this with floats because they do not have an exact dot product. Posits have been used for weather and climate modeling, and they've replaced 64-bit floating point with 16-bit posits and gotten great answers. So that's a 4 times improvement. Now, when you do a 4 times improvement, that's going to be probably at least 4 times faster, but it's going to use even less than 1/4 the energy, 1/4 the power, pardon me, 1/4 the wattage. Now, if you use 1/4 the wattage for 1/4 the time, you get 1/16 the joules. So watts times time equals energy, right? So you can actually get a factor of 16 by doing stuff like this. Lawrence Livermore National Lab compared floats and posits and concluded that, and they were talking about the 64-bit ones. They did shock hydrodynamics. And I used to have a really cool L-shaped demo of this, but it's very dangerous to do animations in PowerPoint. So I just took it out. Anyway, you can see that the posits are doing really well. This is kind of some of the uptake that's been going on underway. And I wish I had my show and tell of a chip that's actually being built and marketed by Caligo Technologies that it runs the full software stack. It's got Python, C, C++, even some applications converted. So you can actually switch over from floats to posits about as effortlessly as it's going to ever be. I think 32-bit precision may actually suffice now for HPC. The very earliest computers, like 1950s, the word size was 36. It was a byte was 6 bits. Can you believe that? So you had 6 bytes per word. And that's, well, they thought it was a good number. I don't know why. But the IBM 360 made the wrenching change in the 60s. They said, let's go to 32-bit. It's just so much easier to multiply by shifting. But it wasn't quite enough. As soon as you took off those 4 bits, what if you could get back those 4 bits? That's kind of what posits do. They have a 28-bit fraction instead of a 24-bit fraction. So that gives you back what you used to have in the 50s, and maybe we can do structural analysis, circuit simulation, computational chemistry. I'm not sure about that computational chemistry. That's probably really tricky. It's a potential 4x cache energy savings or more because of cache effects. I made this joke in Singapore, and they understood it. I want to make single precision great again. I want people to be able to use this and not have to go to double precision all the time. I worry about, especially before a New York audience, even showing that hat. Anyway, we got the 11 design principles, nailed all 6 of these, and we nailed the first 7 through 10. Now 11, we're getting better answers. I don't know what the ultimate, yes, we did it, or no, we didn't, but we're getting better answers than we were. Now, I wanted to see, yes, I have time, great. There's a recent breakthrough in the original model for posits that's proving to be a game changer. See this blue curve? It looks like an Aztec temple. Well, what you do is you limit the number of regime bits in a row. The worst case behavior is like no more than 6 regime bits. So you get 5 stair steps in either direction, and then it holds. So there's a guaranteed minimum accuracy in how many digits do you get. That's even better than floats, because floats, you can actually square a number and then take the square root of it and lose all the significant digits if it lands in, here's my cursor, over there in the RAM. Yeah, and you won't even know it because it's not like it underflowed to 0. It just got really small and then it came back again after you took the square root, and it's off by 50%, way off. The standard posit, as I said, looks like a tent, the pink tent that I've got up here. But the bounded posit means you bound the dynamic range, and I can adjust. I can make all kinds of adjustments to the stair step, and I can really customize this to any number vocabulary you want. I can even tip it one way or the other, or slide it, scale it. So whatever you need for your application, I can fit it with one of these curves. But these things are showing much, much simpler hardware. The encode time is now beating floats at the same precision. I mean, you can see that like a 64-bit B posit takes almost half the time to take apart the exponent and the fraction and then be able to do the standard algorithms. Because once you've decoded the exponent and the fraction, all the algorithms are the same, whether it's floats or posits. You know, shift by this much, line up the binary point, add it, round to this many, and then you re-encode. So then you have to re-encode, and that's on the right-hand side. Is what does it cost you to re-encode in the format? The chip area has now gotten very competitive. Now for the pink one, you can see it was expensive. It just took up to be able to count how many leading zeros or count all those leading ones. If you have to go all the way to the end of a 64-bit number, it's expensive. There's some shortcuts to doing it, sort of like carry look ahead, but either way, you're going to pay for it. But that's gone now. The blue bar graphs are looking just like floats, except better, which means I can put more things on a chip. I can put more processors in a chip if I use posits than floats for the same precision. So if you were going to do A plus B, you've got to decode A and decode B, which you do at the same time. So take that amount of time and you do your operation, whatever that is, and then you re-encode the answer. So I count that once, and I take that amount of power that was used, and I take the amount of time that was used. That should have units of joules. And look how much better the B posit is than the original posit definition. I knew that B posits were useful. I put them in my book, which here's a shameless plug. But I didn't know that the circuits were going to be that much better, wildly better. And that's going to be presented at this year's supercomputer conference in November. We have a paper on this, and I think it's going to make places like AMD say, maybe we need to do this, because if we don't, somebody else might, and we're going to start losing benchmark competitions. So I say, I try to make this material fun. And this is, the publisher allowed me to do every single page in color. And this has got cartoons, it's got memes, it's got limericks. Okay, I'm really pouring it on here, trying to lighten up a very dense and ugly subject of computer arithmetic. And some people have told me I succeeded. I even had a grandmother read it who'd never had any math training. She said, I get it, I can read this, okay? And Einstein said, that's the test. If you can explain it to your grandmother, then you understand it. Otherwise, you don't understand it. I had to use somebody else's grandmother, but I did it. Okay, so in summary, better answers, fewer bits. We can get bitwise reproducibility now because we've got the associativity of addition back. And that really is important for Monte Carlo methods and linear algebra and just a whole lot of things. Posit adoption has caught fire, especially with RISC-V. Posits were invented because this guy at supercomputing in 2016 asked me for something to put into the RISC-V processors that was not IEEE floating point because he recognized that it was inadequate. And he's sitting right there. Thank you, Kurt Kevel. And they allow you to use smaller precisions, and that's always a win. That's how you get another turn of Moore's law. Just get the precision down. Everything's going to get faster if you can use fewer bits. So thank you. For more information, posithub.org.